Okay, we'll next look at the EM spectrum relatively quickly, so look at that one first, and then we'll proceed into polarization and Malice's law. Um, in terms of your electromagnetic spectrum, electric and magnetic fields are oscillating simultaneously in space and time. Uh, so your if we plot your electric field versus position, the amount of distance, because again, your position is in meters, the amount of distance between peaks or between troughs, which is going to be the same amount of time, that is called the wavelength of the light. If you plot your electric field instead against time, you look at your oscillations, the distance between maxima or minima there will end up being called the period, and the frequency is the reciprocal of the period. So that would end up being how much time it takes for how many of them will pass by a point in 1 second, how many maxima or minima per second. The speed of any wave is going to be the product of the wavelength and the frequency, as long as the wave has a unique speed. So you can use the fact that we use c in that equation is intentional because we're thinking about the speed of light. And the speed of light is, in vacuum, the 299,792,450 meters per second. In other media, we'll worry about that a little later down the line. Then the last thing I wanted to mention, because again, most of this is really, really super old hat, so I wasn't wanting to belabor it too much. The electromagnetic spectrum itself, on the table that I wrote there, as you go from left to right, your frequency is increasing, the wavelength is increasing the other way. So radio waves are of the set, those are the ones of the lowest frequency, the ones of the largest wavelength, so in terms of giving you a sense of what some of these are, your frequency for radio waves is probably familiar, because for AM radio it would end up being however many kilohertz. So if you've heard of, whatever it is, if you've got AM 1050 or something, then that's 1050 kilohertz. For FM it would be however many megahertz. So 101.3 I think is ABAX, so that'd be 101.3 million hertz. And all of your radio waves are in that band. Satellite waves are between radio waves and microwaves. Microwaves are roughly your wavelength of a micrometer, which is where that term comes from. As your wavelengths get smaller, frequency gets bigger, you get into infrared. Visible light, the easiest way to remember it is in terms of wavelength. Your violet light is about 400 nanometers, and red is about 750-ish. Keep going to ultraviolet, and then past those you get to X-rays and gamma rays, and the difference between those we'll end up actually addressing a little further down the line, so you don't have to worry a lot about what those are. We'll talk about where they come from later. All right, so now we'll shift gears and go back to looking at polarization and Malice's law. So whenever light will interact with a surface, what ends up happening is the electrons on the surface end up being accelerated by the electric field, so because they're charged. So you end up getting, the electric field from the light ends up since it's oscillating, it will induce an oscillation in the electrons as well. And what happens afterwards depends on the nature of what the electrons do whenever they start to oscillate. We'll worry about later what happens in detail inside the region if light passes through when we talk about refraction. But in the meantime, we'll assume that it's really, really thin. But some types of materials will end up only allowing electric field that's that has its component in one direction to pass through. So the electric field, it will allow it to go this way, but won't allow any of the component perpendicular to it to go through. And materials that have that characteristic are called polarizers. So in general, most light sources, some digital light sources are different. So LED lights sometimes are polarized, but most natural sources of light are unpolarized. So sunlight is unpolarized, direct sunlight at least. And incandescent light is unpolarized. So most non-digital light sources are non-polarized, at least initially. So in that situation, in terms of understanding what happens, if you have light that passes through some plane, so if it's going through this plane, then the light's coming this way. So if the light comes in this way, it has to oscillate perpendicular, because remember, Poynting's vector is perpendicular to your electric field. So the directions that it has available to oscillate are this way and that way. So because that's true, it will oscillate, it could oscillate this way, components, whatever. So it could have, in terms of the number of dimensions, it's got two dimensions, one dimension that way, one dimension that way. So in general, because it's random, because if it's unpolarized, it's doing any of them, then the amount that makes it through is how much of it is one particular polarization direction. And since it's totally random, you got two directions it can go, you get half the light out. Whenever you have unpolarized light hitting a polarizer, half of it makes it through. However, if you end up having polarized light, what will happen if you've got one that's polarized this way and one that's polarized at an angle to it, then the amount of light that passes through, if it's polarized in this direction and your other polarizer is this way, then it's the component of the light that is going this way. So if it's polarized, all of it's bouncing in this direction. So it's how much of it is in this direction that can eventually go in this direction. So if how much of it will end up this way, and notice it's the component, because you can't get any for free. So it's only the part of the electric field that has a component in this direction. And we know how to find components. So in this situation, you think about, okay, this one is your source, so it's oscillating this way. And then this is, let's say, your x direction. So to find how much of your component is now in the new direction, you end up taking this amount times the cosine of the angle between. So that's how much electric field will end up making it through. Now, from what we talked about earlier, remember your intensity is not proportional to your electric field. It's proportional to the electric field squared. So because that's true, the intensity that ends up making it through is the intensity before it reaches that polarizer times the cosine squared of the angle between, because intensity is proportional to the square of the electric field. And that fact, so polarized light hitting another polarizer, the amount that passes through is the old intensity times the cosine squared of the angle, is called Malice's law. So I gave an example there. Let's suppose that we end up having that sunlight at zenith is 1400 watts per square meter, and sunlight, as we said, is unpolarized. So we end up sending sunlight through two polarizers. It comes down this way into the first one, and then we have another one at an angle at 37 degrees between the two. So I want to know how bright the light is coming out the bottom. So you got sunlight coming in here, it passes through, so it cuts down part of the light, then it passes through another polarizer, which cuts down more. So I want to know how much intensity I have whenever it gets all the way down. So in that situation, to end up finding it, I have two parts. The intensity of the light that hits it gets cut in half by passing through the polarizer. Sunlight gets cut in half because it's unpolarized before. So then you get half of it through the 700 watts per square meter, and then to find how much makes it through. Now it's 700 after it passes the first one, then multiply by the cosine square of the angle between the two polarization directions, which is given as 37 degrees in this problem. Multiply by cosine square of 37 degrees, and you come up with your final answer of 446 watts per square meter. All right.